All right, here we have a composite system of two converging lenses, and notice that we're given the two focal lengths. They are separated by a distance 6x. We're given that as well. We're told that the lens on the left has the longer focal length. This is a problem that would just be given in language, and then the idea is the student would read the problem, parse it, and be able to draw a diagram as well. We're told that there's an object 4x to the left of the left-hand lens, and then we're asked to locate and describe the final image. So this is a common question where you're given a physical scenario, composite system, an object, and asked to locate and describe your final image. So we just do this one component at a time. So light will leave the object and go to lens 1 first, and we're going to solve this in order here. So lens 1 is where I'll begin. And my object distance there is given to me, 4x. It's positive, it's on the side of the incoming light, and I want to solve for my image distance. Now over on the right-hand side in blue here is my general equation involving F, P, and Q, and then notice that I solved that for image distance right away, just because I know this is the equation I'm going to be using. I don't want to solve it over and over again. So I just do this once right at the very beginning, and then I have this at my disposal here to use. Okay, so when I'm solving for this, basically this is going to be P F over P minus F here, right? So 4x, 3x, these are converging lenses. They have positive focal lengths. 4x minus 3x. So that gives me 12x. This is positive, right? So that means it's to the right of lens 1. So if this is 6x, that means I'm going to kind of do a jaggedy thing here. And I'll say, here's my image 1. And it is 6x from the second lens, because of course this 12x is given with respect to lens 1. Remember that the image and object distances are always given with respect to whatever component you're working on. This is one of the reasons that I'm really clear about which component I'm working on. I label that above my work so that I know that those distances, I can refer them to the component and know where I'm talking about in real space. Okay, cool. While we're here, let's go ahead and crank out the magnification. This is another way you can do it, is just do it as you're going through. So that's going to be negative Q over P, of course. So negative 12x over 4x gives me negative 3. So I see that I have an inverted magnified image 1. Okay, but we're not done. We're going to go and look at what happens as we go through the second lens, because we have another lens. So I'll just prime this. My object distance for this lens. Now my object for lens 2 is the image that was formed by lens 1, so that'll be image 1. Notice that that image is to the right of the lens. And for this particular problem, there's no mirror to bounce the light, to change the direction of the light in this problem. So my incoming and outgoing light, right? Light goes from left to right everywhere. So let me just be really clear. For lens 1, it goes left to right. For lens 2, it's going left to right as well. Again, there's no mirror in this problem to bounce the light back the opposite direction. What that means for us for this object distance is that this is going to be a negative object distance because it is not on the side of the incoming light. So this is actually going to be negative 6x. Remember that it's always measured with respect to the component that you're working with. And since it is not on the side of the incoming light, it's a negative object distance. So let me solve for my image distance now for lens 2. So that's going to be negative 6x times my focal length, which is 2x, all over negative 6x minus 2x. So this gives me 3x over 2. Now this is positive, right? So that means that it is on the side of the outgoing light. It is on the side of the outgoing light. So that's going to be, say, like right here. This is image 2. That's our final image. And it would be 3/2 x to the right of the lens. So that's this distance here that we're talking about, right? That is, I'll just label it as q prime right now, 3x over 2. So it's located to the right of lens 2. Let's go ahead and crank this magnification here. That's going to be negative q prime over p prime here, which is negative 3x over 2 divided by p prime, which is negative 6x. So that gives me positive 1/4. So that's upright and diminished, obviously. Okay, cool. So we just have those two components. That's all we're looking at because, again, there's no mirror to move anything around. So where is my final image? We're going to locate it. It's at the position of image 2. So my final image here is 3x over 2 to the right of lens 2. So remember that just having the image distance is not the same as locating the final image. 3x over 2 isn't meaningful unless I tell you it's 3x over 2 to the right of lens 2. Then you know exactly where to draw it. Let's figure out our total magnification. Here it's going to be the product of M1 and M2. So negative 3 times positive 1/4. That's going to be negative 3/4. That's my total magnification. So this tells me that my final image is inverted and it's diminished, right? Diminished by 3/4. And the only thing we haven't answered about our image yet is if it's real or virtual. But if I look at, again, what we focus on for real and virtual, let me switch up colors here, is we look at the very last image distance. So if I look at that, it's positive. So I know that the final image is going to be real, and that's because q prime is greater than 0. Again, it doesn't matter if any intermediate images are virtual. You just, for this one, you just look at the very last image distance and you ask yourself if that is greater or less than 0, and that tells you if your final image is real or virtual.